Of the shim coils, the purpose of the shim coils is to tweak the BO, which is the acronym or the initials for the main magnetic field. B0 is the main magnetic field, to get it as perfect as possible. Just like shielding, you have passive shimming and active shimming. Passive, if you put a piece of metal on the bore of the magnet is going to be pulled just a little bit more toward the metal. So that is a form of passive shimming. Active shimming is you actually have coils, and another set of coils inside the bore of the magnet that help reverse the polarity just to tweak that main magnetic field. Remember, the purpose of shim coils is to tweak the B0 value, your main magnetic field value, to get it as perfect from one end of the magnet to the other, from one side to the other. So why is shimming important? Why even bother having shim coils? First of all, shimming is a process of making the B0 field homogeneous or homogeneic. The main magnetic field, if you have to start with something that's even and known, the shimming is measured in parts per million. Superconducting magnets are shimmed better than permanent magnets because of its superconducting nature. But what makes it go out of whack anyways? The reason some magnets are not as homogeneic as others is because you have metal in the room. People think that it's just the metal that's attracted to the magnetic field, and that's false. Think about it. If the magnetic field is pulling a ferromagnetic object toward it, it is reaching out toward it, trying to grab it. So think about it as fingers. The magnetic field reaches out and tries to grab anything that it can to bring it toward it. When it reaches out like that, the magnetic field is no longer homogeneous. So it's torqued. Every chair that has a screw in it, every picture on the wall that has a screw in it, affect the magnetic field, and the shim coils are there to tweak it back into a steady state. And just like I said, just like shielding, shim coils or shimming is done both by active and passive measures. Now, active shimming, just like active shielding, is a reverse polarity magnet. It requires a superconducting shim coil of wire within the cryostat, which is the tube housing, usually attached to some metal. These coils are spaced on a cylinder with electric current and polarity passing through them. Remember the law of electromagnetism. A charged particle moving along a path creates a magnetic field perpendicular to the direction of the particle's motion. So it's easy. If your second, third, fourth, fifth fingers are going in the direction of the particle motion, your thumb will tell you the path of the current, or excuse me, the path of the magnetism. So active shielding, all it does is create opposite pathways. That way you can kind of torque or tweak the magnetic field. This is done on installation and not repeated unless something happens with the environment. Passive shimming, just like passive shielding, means you're putting metal plates or steel plates somewhere. In this case, we're using metal plates placed on a cylinder within the magnet. There's a probe in the magnet that measures the magnetic field, and it tells the engineers where to put these plates of metal. And what does it do? Just like I explained earlier, the magnetic field is drawn toward that steel, that ferromagnetic object, so it pulls itself out, not just pulls the object in. Alright, so now let's get to the meat of the magnet, the gradient coils. The purpose of the gradient coil is to torque the B0. Remember, B0 stands for your main magnetic field. We torque it in order to perform spatial encoding. The gradient strength is expressed in units of Gauss, which is GAUSS per centimeter, which is equal to 10 millitesla per meter. If you're looking for a quality metric of a magnet, a good gradient will work at 15 or 40 millitesla per meter. Now when we start talking about gradient coils, I want you to stay with me because this can get confusing very fast, but when you think about it and it's broken down, it is simple. There are three gradients: the x gradient, the y gradient, and the z gradient. These three gradients work together to make your image matrix. One of the three will always be your slice selection gradient. Depending on if you want an axial, a sagittal, or coronal slice, one of the three will always be assigned for your slice selection. The other two will be one for phase encoding and the other for frequency encoding. We'll get into what phase encoding and frequency encoding are later on in our lessons. All I want you to know at this point is that there's three gradient coils. One will always determine or be selected by which type of slice you're going to acquire, axial, sagittal, or coronal.